Good morning.
Morning, Doug.
Morning.
Are you guys all laying in bed? Is that why I never see anybody? Cheyenne had to get up to come down to the computer, so I always get to see her. But you guys are laying on your pillow right now, aren't you? There's like a phone in front of your face. You're trying to stay awake.
No, I'm at my computer.
I'm on a tablet, so my camera's not the best.
I'm not gonna play music anymore when I come in if you guys don't start waking up. Dark Days. Have you heard this song? I get all my good songs from my daughter. She sends me texts with good songs. Dark Days, Local Natives. This is a good one.
I have not heard that.
There's the most important thing I'll show you today. Who cares about calculus?
Okay, see you later.
Are we gonna have homework for the 11.2 section? Because I don't see it.
Yeah, that's a point you're making there. Let's go fix that right now. All right, I want to start off with something just quickly from yesterday, and I'll go fix that right now while we're talking. I don't really want to turn this music off, but I guess I have to. So Martin asked a good question going out the door yesterday, which I didn't know the answer to. And we were kind of talking about it quickly as we went out. Ben said he thought it worked, and I just wanted to type it in real quick. But I showed you yesterday this problem where we had 8 over 1 minus 4x and the whole quantity was squared, and it turned out that was a ridiculous can of worms. And we saw that if you took the integral of it, and then it would produce the formula that looks kind of like it's supposed to look, and then we were able to succeed with it. But Martin was kind of asking the question, well, man, if you squared that thing out, in other words, let's square this mess out. Isn't 1 minus 4x squared, isn't that 1 minus 4x, which is minus 8x, and then 4x squared is 16x squared, right? Isn't that what it is? Yeah. And so his question was, hey, isn't that in the right form now? Like, there's your a up there on top, it's 8, and isn't this entire thing, like, couldn't that, because it's 1 minus junk, right? So why couldn't this whole thing here, notice if I make this whole thing here look like that, I would have to change that sign to a negative since it's now minus everything. So his question was, well, couldn't we just let that be the x? So then a is 8, bing, and then x is, well, that mess right there, and it's raised to the nth power. We'll notice the answer to that appears to be yes, because look, they're a good fit. And notice I had 12 terms in it, so that's quite a few terms. And so as per usual, if I go here and look at 0, it's like, yeah, they're almost indistinguishable. So it's like, why do all that integral nonsense? But take a look at this. Like, if you were to expand that out, do you understand how sort of problematic that is? It's not wrong. That's a true statement right there. But if you expanded this out, remember you have 8 times this to the 0, and then you have 8 times this to the first, and 8 times this to the second, and third, and fourth, and fifth. Well, as an example, notice when you have 8x minus 16x squared to the second power, that's pretty ugly. It's like a parabola squared. And so if you wanted to write it, well, nice and simple, like a power series is, where you just have a 1x term and 1x squared term and 1x cubed term, so that it's easy to plug something in. Notice that's going to be really messy, because you're going to have to square 8x minus 16x squared, and that's going to produce a squared term, a cubed term, and a 4th degree term. And then when you raise this to the third power, that's going to produce another cubed term, a 4th degree term. And so every one of these terms is going to have a whole bunch of squareds and fourths. And so it actually is okay to do, but in a sense, it doesn't come out as clean. And so that's just kind of interesting, just kind of fun to play. So, and then the other thing I don't want to investigate, but notice that interestingly, that seems to like want to model both sides of the graph almost, like it's like a good model over here too. So, you know, I find myself a little curious about that, like, you know, what's going on with that. But anyway, that's a side story. So quickly, while I'm thinking about it, because this might come up again, so I just want to show you. I think I'm ready to kind of post all of this, but I don't think I have the 11.3 assignment turned on, and that's what we're about to talk about. This is not the right place to do that. So we're going to talk about today, my friends, is something much more cooler, which is how to do this for everything. Show by dates.
It was the 11.2 that's not visible.
Got it, 11.2. That's on purpose. I turned it off. Because we are not going to do 11.2, at least not an assignment in 11.2. So what 11.2 is about, let me share a screen while we're talking here. What 11.2 is about is that radius of convergence concept. We've talked a little bit about how important that is, because we said these aren't the same unless you stay inside a certain region. So we're saying they're the same, but they're not kind of the same everywhere. And so 11.2 looks at that a little more formally. Now we might go back and, you know, answer it, but what I'm hoping to do is actually talk about it in the context of real questions, because I feel like books actually ruin this section, and that's why we're effectively going to take a little bit more time with this, and today will be a good example of, if you will, the benefit of that. So let's do it. Let's see, this is the wrong notebook. This is not. So I want to start off with modeling something that, well, all the little tricks we came up with yesterday aren't going to work for. And that's where this starts to get fun. What's going on with the old screen mirroring problem here? Seems to be not behaving. Let's double check and make sure we're on the right network, since that's been a problem before. We are. Let's try it again from the start. So I want you to consider the function y equals, or f of x equals, the square root of, let's see, where are we going to start with this? So I think we'll start with something from calculus 1. So 11.3, I'll title this later on. But back in chapter 4.6, we did something that I alluded to the other day called linear approximation. And so this is an example really quickly of kind of what we did back in that section. We said something like, I don't have a calculator, I'm a caveman, and I want to know what the square root of 3 is. And I don't know that. Again, this is, again, don't forget, people didn't have calculators forever in history. And so, they want to know about what the square root of 3 is. And so what they said was this: well, why don't we take the equation y equals the square root of x? And we know that the square root of x looks kind of something like this. And we'll just kind of find the equation of a line that models it. And this is what we've been seeing. That's what we've been seeing for all this past week, is like how to get one equation to look like another one. Except what we're going to do here, though, is model it just with a line, like a really kind of low school. And so we would say, okay, well, I don't know what the square root of 3 is, unfortunately, but I do know what the square root of 4 is. So let's go there. That's the square root of 4. Well, if I put in x is 4 and I take the square root of it, I get 2. So that's the 0.42 up there. And then what we'll do is we will find the equation of that line tangent to that curve. And then we'll plug 3 into that line. Does that make sense? So this line, we'll say this line's going to be f of x, and then we'll just go find f of 3. And notice from the graph, we can tell that that's going to be close. And it's even going to be a little too big. Isn't that kind of cool? We actually know our answer is going to be a little too high for that. But I'm just picking something kind of nearby. So we said, okay, well, how do you find the equation of that line? Well, I know the 0.42, so there's something. But what else do I need? What else do I know that calculus tells us that'll help us find the equation of that line? Can you answer that?
You know, the slope will be rise over run.
Exactly. Calculus lets us find the slope. And so since I know that square root of x is the same as x to the 1/2, then I can say, sweet, y prime is multiply the 1/2 down front, take 1/2 away from that. That looks a little more beautiful if I reread it like this. Oops. Yeah, I guess that's true. It is a 4, but for now, that's our derivative. And so then we say, okay, well, I know what the slope is at 4. 1/2 times the square root of 4 is 1/2 times 2, which is 1/4. And so I know the slope of my blue line is 1/4, and now I have everything I need to find the equation of that line. Y equals slope times x plus b. Notice it's going to hit right over there somewhere. And we know that when y is 2, x has to be 4. So that would be 1 plus what is 2? Well, that'd be 1. So I found the equation of the line. It's 1/4 x plus 1. This is a model of the radical equation. It's a model of that. Well, it's a model as long as what? It's a terrible model, actually, but it's a pretty good model as long as what?
You're at 4 or around 4.
Exactly. Every time you talk, Raymond, I always think I can't improve on what he just said. As long as I'm near 4. Terrible model if you go outside of that. But isn't that what we've been talking about lately? That kind of radius of convergence idea. In other words, hey, this graph is a great graph, but it's got to be really close. We got to be close to something. And so this only works around 4. And so I say, if I'm a caveman, I say, dang, I don't have a calculator yet. It's not the year 2000. So I don't know what the square root of 3 is, but I do know how to plug 3 into my line. Like, notice it allows me to get an answer by just doing basic math, right? I don't have to take a square root. I don't have to use these complicated functions like sines and cosines. I'll just use a line. 1/4 of 3 is 3/4 plus 1 is 1 3/4. So it's like, so you would say, well, f of 3 is 1.75. But basically the square root of 3 then we'd say is approximately 1.75. And based on the picture, as I said, we even know that this is a little bit too big. And of course you bust out your machine, since you are lazy rich people in the 21st century, and your calculator says the square root of 3 is actually 1.732. And so it's like, well, yeah, that's actually pretty awesome. That's only off by 2 100ths. That's pretty cool, isn't it? And not only that, we knew it was too big. So we could have even kind of just in our mind rounded it down a little bit, right? And so that's what calculus does. Well, what are we really doing today? We're just going to step it up. Do you have to stop the model? You already have the answer to this question. Do you have to stop the model at a line? Like, what if we modeled that with a parabola? Doesn't a parabola want to curve? And so if I model this with a parabola, wouldn't that even be better? Wouldn't that give us a better estimate? Let's kind of quickly do that. And I want to entirely do this from scratch. What if we used a parabola as a model? Well, you might think that's a little harder to find. Like, how am I going to find the model of a parabola for this? I know what a line is. Y equals mx plus b, like m is the slope. And so derivatives allow us to find the slope and all of that. And so I kind of know how to do it but how am I supposed to find a parabola, which we know looks like this? Y equals ax squared plus bx plus c. We know parabolas look like that. And unfortunately, we don't know much about those. In other words, what is a? Well, it's not the slope. What is b? The only thing I know is c is the y-intercept. And And, you can probably guess that, our parabola, if we don't screw it up, is, maybe going to look something like this. I don't know. Maybe it'll do that. So, if the y-intercept of this turned out to be 1, then probably this y-intercept will be a half or something like that. But it's not like I know what it is. And so don't you feel like I don't know what to do? Like that'd be great if we could find one, but how am I supposed to do that?
Are we looking for a parabola that goes through the 0.42?
Yeah, we needed to go through the 0.42.
Could you take like a theoretical derivative and then set the derivative equal to 0 when x equals 4? So like keep your a and b and c because we don't know what that is. Oh wait, never mind. That wouldn't work.
Well, you're going down the right road there, Eve, because it still has to do with slope. In other words, would you agree this is still true? Like our parabola at 4, we'd still like the slope to be a 4th.
Could we do curve fitting and maybe make another point along the square root of x?
Yeah, now notice, could we do some kind of a curve fitting concept where we took I think I'll erase this so I'll make it big, but like we just found some other point over here. We found a point kind of here and here. Now we have 3 points. Notice our equation has 3 unknowns. And so if we had 3 points, then we could find our equation. The problem is I don't really know any other points. Like I know the square root of 1. Again, we're trying to do this without a calculator because we don't need it. We don't need this to find the square root of 3, right? We have a calculator, but what we're trying to do is find a model for this. And so the other points are difficult to come by. But having said that, yes is the answer to that. You certainly could. But wouldn't you find yourself saying, well, I'll find the square root of 3 and the square root of 5, and then I'll have 3 points, and then that'll make a parabola through those? You're exactly right. But then you'd be taking the square root of 3 and the square root of 5, and so the easy way, or where this actually turns into something that's effectively a whole lot more powerful, is continuing with this idea of slope. So would you agree that I need y of 4 to still be, I need that to still be 2. In other words, I need it to go through the 0.42. And I need y prime of 4 to still be 1/4. I need the slope to match 2. In other words, I want the slope of my curve to match the slope of a square root equation. I mean, that's going to make sure the point is at the right point and the slope is at the right slope. And all we have to do to get a parabola is just go one more level. What about the second derivative? This is easier, is what it comes down to, than some of the other ideas that some of you expertly proposed. And so, well, what's the second derivative? I know the first derivative, we said a second ago, was 1 over 2 the square root of x, or I'll rewrite it in the form that it was in. It makes it easier to take its derivative. So if I take a derivative of that equation, then the 1/2 gets multiplied by the 1/2, and that becomes negative 1/4. And then I subtract 1 from that, so that becomes negative 3/2. So there's my second derivative. And again, I could write that a little nicer if I wanted to, I guess. 1 over 4 times, I guess that would be the square root of x, since there's a 1/2 on the bottom. And then that would be raised to the 3rd power. Again, just get your calculator out, but okay, well, if that's true, then what's the match for a second derivative? Well, if I throw a 4 in there, the square root of 4 is 2, 2 cubed is 8, 8 times 4 is 32. So does it make sense that if it was to match this right here, is going to make it match the y equals square root of x graph? It's going to make it match that as good as you can match it. Does that make sense? Now from Calc 1, what does the second derivative tell us? Like I know the first derivative tells me slope.
The inflection point?
It can allow you to calculate the inflection point. What does it mean that that's negative?
Is
I
it
think
the
it's
slope is downward?
Is it like concave down or something?
yeah, concavity, I think.
Yeah, remember how you have like stuff coming back to your mind? It's kind of you're brainstorming right now. It's like, again, that was only like, this is why I teach the way I do. That was only like 3-4 months ago, but notice it's like gone, right? Like it's sort of hazy. So, you know, we got to get it back a little bit. Yeah, that's normal. But if you take the derivative of something, that's change, right? But in this case, we took the derivative of slope. And so what's the change of the slope? Well, if the change of slope is negative, then doesn't that mean the slope is getting smaller and smaller? So it's like, yeah, I know what the slope is, but I also kind of need to know how the slope is changing. And this is telling you the slope is actually getting a hair smaller. And if you look at the graph, isn't that actually true? Come on, man, let me zoom. Isn't the slope here 1/4, but then as you move to the right, isn't it getting a little smaller? In other words, it's leveling off. And so that's actually kind of cool information to add to this. It doesn't feel as natural as slope, but we're adding that to this. Well, the question is, how does that help us? Watch this carefully. Well, and this is where Eve's idea will actually come to some fruition. Like she just, you know, popped it out there and hadn't fully thought it through, but isn't this what our parabola looks like? And so if I take its first derivative, then I can take the derivative. And again, remember that A, B, and C are in the set of constants. Again, you should start learning advanced math symbolism. That E looking Zambridis is in the set of, I think. All of a sudden I'm thinking, yeah, I think that's right. So y prime, I know what the derivative of a times x squared is. It'd be 2 times a times x. Remember, a is like 5 or 7 or any other constant. It's just along for the ride. The derivative of bx, or like 7x or 8x or 9x, is just the constant. You agree that's the derivative? I don't know what a, b, and c are yet, but isn't that the derivative? And secondly, what's the second derivative? Well, the second derivative, the b is a constant, so the derivative of that's gone. The derivative of x is 1, and so I just get 2a. We'll scope this one out. This one right here actually is really easy to solve because there's not as much junk left in it, right? So doesn't that mean, hence, that 2a would have to be equal to, well, doesn't our second derivative at 4 -1/32? So then we'll go pick an a. The only thing that contributes to causing -1/32 for us, we need it to be 1/32. Since the only thing that survived 2 derivatives was that a, is that. So if I solve that, then I get, bam, a is -1/64. I actually just found a. Now backtrack once. Y prime. Well, remember, all of this happened when x was 4, right? We were concerned about x is 4. That's the point at which we're interested in. And so when x is 4, we actually know, we now have everything we need to know to get b. So y prime of 4, we said, needed to be 1/4. And we now know that that's got to be equal to 2 times a, which we just figured out is -1/64, and that's multiplied by x, which is 4, plus b. I can find b. Let's see, what would that be? That would be 8/64, which is an 1/8. So I'm actually adding an 1/8 to a quarter. It's 3/4 or 3/8. I don't even need to use a calculator. This is beautiful. Life is good. So I just found b. And now that I know those, couldn't I find C? Because again, we know y of 4 is 2. So if y of 4 is equal to 2, that's our y coordinate, and y coordinate is equal to ax squared plus bx plus c. And we already figured out that a was -1/64. And we said we were concerned about this when x was 4. And we just learned that B was 3/8. And again, we know that X is 4. Well, there's only one thing left for C to be, for that to be a true statement. And so do you see how we're using slope and actually just continuing to use slope? The slope of the slope. And of course, this idea is going to keep going. That's what's so cool about it. We could find a cubed equation using the same technique in a 4th degree, in a 5th degree, in a 6th degree. Hey, isn't that what we've been studying? Like, isn't this a power series? Isn't ax squared plus bx plus c, isn't that just a power series? That's a polynomial, right? Except now we're modeling something that doesn't fit the pattern. That doesn't fit that a over 1 minus x pattern. We're actually just giving that up and saying that's kind of old school. We're just going to go do this for everything now. Let's see, 2 plus 4 64ths. Didn't I already write this down somewhere? I don't think I did. 2 plus 4 divided by 64. And then I will subtract 12/8 from that. If I didn't screw this up, I got 0.5625, which is 9/16. So doesn't that sound right to me? I don't know. 2 plus that minus that. I think it's right. So actually, I think I just found a parabola, not a linear approximation of the square root of x, but actually a parabolic approximation. Please tell me if you see anything I did wrong.
I got 3/4 for C.
4/64 minus 9/16 doesn't sound right to me for some reason, but I don't see that I typed anything wrong.
Was the 4 squared there?
Oh, there is something wrong. See this 2 right here? I forgot it.
Oh. Oh.
So wait. Oh, the 4 is squared. Yeah, it's 16 times 64. Yeah, I screwed it up. I was gonna say that didn't seem right to me for some reason. I didn't square the 4, right? Everybody see that? Incidentally, if I'm all by myself, how am I going to catch that? How would I catch this?
You graph it.
I graph it and it won't look right. Does that make sense? So there's A, there's B. Is that what you said you got, Ben? 3/4?
Yeah, that's what I got.
Okay, good. And finally, 3/4. And so we're saying this is actually, if you will, a parabolic model. And I don't know about you, but it's like, oh man, I'm excited. I want to see this baby. Is this really true? So let's look at both of our models. Let's see, we had, where did our model go? There it is, 1/4 x plus 1. Let's go into Desmos. So goodbye. So we're trying to model the square root of x, which we know looks like that. Notice the window is all jacked up. So from the previous time we used this, if I hit zoom square, that should actually get us more reasonable. Okay, I'm happy with that. And then we said our model y equals 1/4 x plus 1 was good. And you know, now we can see, yeah, that is good. And remember, we were trying to figure this out at 3 and notice, yeah, look how close those are. That's why we got such a good answer. So the purple said 1.75 was the answer to the square root of 3, whereas the actual green answer was 1.73. And so really cool. What's going to happen if I didn't screw this up now? Somebody put that into words. What's going to happen if I don't screw this up? Bam, even better. Wow. I wonder what answer that's going to give for 3. Notice how how ridiculously good that looks. And as you know, if I cheat and go back here, and instead of calling that y, I call it f of x, then down here I can say, what then? Let it do the work for me. What's that value at 3? Again, bust out your calculator. What's the square root of 3? It's 1.732. We're now only off by 2 thousandths. That's amazing. What a cool estimate. And how did we get the estimate? We just multiplied and subtracted and added. I mean, isn't that kind of cool? Like we actually got the square root of 3 and we never had to use the square root. We just added and subtracted.
I forgot the name, but last term we went over the proof of I forgot the name of the method. It was for like estimating under the curve, but we used, it's kind of the same thing, right?
Let's see, what are you referring to?
We used curves instead of rectangles to estimate the area under the
Oh,
curve.
yeah. Simpson's rule. That's exactly right. In other words, instead of making boxes underneath curves, which is like a stupid fit for a curve, we said, how about if we put parabolas connecting the points under a curve? And Simpson's rule gave us a cool way of coming up with an area without ever having to take an integral. So yeah, I'm glad you remembered that, Martin. And so this is kind of the same. So isn't this powerful? And of course, you can see where this is going, as I said, because does this have to stop at a squared equation? Now you can appreciate if the goal was to find the square root of 3, we're probably good enough. Like we don't need a cubed equation. We're within 2 thousandths of the right answer. And again, that's because we had a calculator. So keep this in mind, because there's a little discussion about estimation in this in 11.3. The only reason we know it's off by 2 thousandths is because we have a calculator which tells us the correct answer. So keep in mind, if you're a caveman, anytime before 30, 40 years ago, nobody knew the right answer. Like in a sense, nobody knew what the square root of 3 was. Isn't that weird to think about? Like, but even we don't know what it is. Just because your calculator tells you that, 9 decimal places doesn't mean you know the answer either, because it just keeps on going. Remember, that's what irrational means, irratioable. You can't write it as a fraction. So actually nobody knows what the square root of 3 is. We just think we do because we have 9 places. But for them, they said, okay, well, I have an estimate 1.734. But then they began to wonder, like, how much can I count on that? Like, is that close? And so, if you could come up with some trick or some formula, it would say, well, I know for sure it's less than 5 thousandths. I don't know how much less. I don't know that it's actually only 2 thousandths off, but I can guarantee it's less than 5 1,000ths. And that way you could say, okay, good, that's close enough for me. I'll stick with that one then. I don't need a cubic equation. So they would never know. Isn't that weird to think like they got an estimate, but they don't even know how good it is? They have no way of checking.
But didn't we just prove with this that it is in fact 1.73, like for sure?
Why do you say that? Because you're right.
Well, because we confirmed mathematically adding and subtracting that we got 1.73, but our thousandths place is the one that's off. So we can't for sure or trust the calculator. So we know for sure it's 1.73, right?
Yeah. And I thought where you're going with that is like we did the line and we got an answer and it was 1.7. And then we did the parabola and it was 1.7. So does it make sense? The 1.7 is for sure correct. And so, yeah, based on what you just did immediately, you can kind of see the progression. And that's where these formulas ultimately come from, is somebody saying, hey, what's changing as you move from a squared model to a cubic model to a 4th degree model? So 2 important things just happened here. One of them is we just did this for an equation that looks nothing like a over 1 minus x. Remember how hard we worked yesterday to make equations that didn't look like that? Remember how amazing of a brilliant idea it was that we had the natural log of something, and some genius thought, hey, if you take the derivative of that, then all of a sudden it looks like a over 1 minus x. And then we were able to kind of make it happen. We're not going to get the square root of x to look like 1 over 1 minus x. Do you understand that? So we just did this for an equation that looks nothing like the pattern. And secondly, every time we check the 2 graphs to see where they look the same yesterday and the day before, where did they look the same? Where did we have to look?
At 0?
It was always 0. Does that make sense? And so like in our case, we just used this to kind of see what the square root of 3 was by looking at 4. And so notice they look the same out here at 4, right? That's where they look the same. And so we just went to a new location. So that's actually kind of powerful. And then the only other thing I want to say is that was a lot of work to get it to match at 4. And so what if we said, let's start over and let's try to make it match. Let's say you wanted the square root of 8. And so then you went out to 9 because 9 is closer to 8, right? Because this would be a bad model to use for the square root of for the square root of 8, right? Because even the black one is off by the time you get out that far away. Like, and again, that's the radius of convergence idea. It's like it isn't good to go that far away from 4. Don't go 4 away from 4. That's too far away. Out at 8, they're not a good model anymore. And so does it make sense we'd have to redo this whole thing if we wanted a different model, if we want to go out to 8? So we said, hey, let's do this not at 4, let's do it at 9, because that's really close. That's like a close neighbor, and we know the square root of 9. So let's go there. Well, we'd have to start over. We'd still get a parabola, but it wouldn't be 1/64, and it wouldn't be 3/8, and it wouldn't be 3/4. Every single part of that would be different. We just have to start over. So what we're looking for here ultimately is kind of a pattern for this. So keep that in mind. I will throw this in the notes since I took the trouble to do it. And now I'm going to show you something kind of cool. So
For some reason, I'm having like flashbacks of us doing this in like Calc 1. And I don't know if it was just traumatizing or I don't know, but I feel like I'm having flashbacks to we did something similar where we had to actually no, it was Calc 1 because we had to approximate like e to the x and natural log because we were like, oh, we don't actually know it.
Yeah, can you remember? Because I actually don't. When you say that, I'm not remembering where we were doing that or in what context right now. Are you?
Nope, I just remember calculating it.
Yeah.
And I think we were doing like the square root of 49 for like the square root of 50, and you had to approximate it to so many decimal places.
And
or something.
That's exactly, I think, what I was referring to. 4.6 was doing linear approximation, and so we did it. It's just that we only used a line. That's kind of the idea. We went near it, but we found the equation of a line, and it was an application for derivatives because we needed to take the derivative, as I kind of boxed in right here. We needed to take the derivative to get the slope, and so that's why it was an application for derivatives. And so I'm pretty sure that's what you're remembering. So y of 3 then is apparently 1.734. Wow. Off by 2 thousandths. That's good. That's a good estimate. So we found a parabolic model for something. Well, the idea, and again, do you notice that this is a power series, isn't it? Isn't this exactly what we've been studying, power series? So there's a power series. It's got a constant, and then it's got an x term, and then it's got an x squared term. We're used to kind of writing those recently backwards. In other words, where you start with a constant, and then you proceed up from there. Let's take this to, let's do one more example that's really kind of similar, and I'll show you something kind of neat. Now, the fact that we were at 4 that time actually made it a lot more work. So I want to show you something kind of cool here. So let's consider another example. And let's try to find a model for the square root of x plus 4. Why did I pick 4? I'm trying to remember if that matters. I'm just thinking we just did 4, so I don't want to do 4 again, but let's do 4 again anyway. So, fine. Now, you should know, and this is very important to remind yourself of, what is that for? It's the same graph we just did. It's the square root of x, except what does the plus 4 do?
It shifts it to the left 4 spaces.
Shifts it to the left 4, and that's plus 4. So you might think, oh, it'll be right 4. No, it's left 4. So that's the same graph. It just slid left 4. But This time we're not going to go at x equals 4. We're going to go at x equals 0. Now, what this will do is save us a bunch of trouble. So at 4 meant we had to plug a lot of stuff in a minute ago. If we go at x is 0, so this is now going to look just like it did yesterday. It's going to look exactly the same at 0 as the square root graph. Now, the other thing we're going to do is crazily, and this is where you're going to see the pattern to this for the first time. We're going to model this one not with a quadratic, not even with a cubic, but a quartic. What does that mean? What's that code for? Fourth. Why is what I just did not so good? It was working really good till right here. Do you agree with that? Because
Yeah, that's a lot of terms we have to find.
we got a lot of terms. We got 5 terms, and then that last one, because it's E, well, like we've used that letter, right? That's a thing. That's like 2.718, and so that's kind of a bummer. And again, this is why mathematicians don't use, or why we talked in this last section about not using letters like this. We just call them C0, C1, C2, C3, C4, C5. That not only that, it helps you know which one is which. In other words, if I called this one C4, then it'd be like, oh yeah, that's the constant that goes with the 4 in the power series, right? And so we'll get to that, but I'll just leave this alone. The only thing I am going to do though is go back and change this. I don't want to use F because that looks like function. G, H, I, J, K.
I like K.
Yeah, let's do K because K looks like constant. Let's go with K. I like it already. Okay, now here's where it gets really cool. Watch this. So we saw the pattern that derivatives were kind of important in all of this. And so let's just cut to the chase and sort of go find all of those. Well, let's see, I'm going to rename, so they're not both named Y. I'm going to call this one f of x. So the original equation was y. So let's go find all of its derivatives. So we have y, which is the square root of x plus 4, and y of 0 is the square root of 4, which is 2. And then we have y prime, which is 1 over 2 times the square root of x plus 4. And I think I'll kind of do this off to the side over here. I'll like do the math. So this is really x plus 4 to the 1/2. And so we bring the 1/2 down front. And then we subtract 1 from that. And so, yeah, I got that right. I have, this is the, what I'm writing on the left is kind of the nicer derivative. And now if I go plug 0 into that, notice it's easier to put 0 in. I have 1 over 2 times 2, which is 1/4. And then the second derivative would be the 1/2 gets multiplied by the 1/2, making 1/4. And now the x plus 4, you subtract 1 from that. Now it's up to minus 3/2. And so again, I don't really know how to write this, but I think I'll write it as negative 1 over 4. And I'll just write x plus 4 to the 3/2. And so y of 0. Do this in your head. So if I have, so this 2 right here means square root. So the square root of 4 is 2, and then you have 2 cubed, which is 8, and then 8 times 4 is 32.
My gut's telling me negative 1 over 32 because that's what we previously got.
Yeah, this is the same exact graph, and that's what I pointed out. We just slid that left 4 places, and then we evaluated it at 0, and so we're getting the same answers for the first 3 questions that we got before. So that's just a coincidence. It doesn't really matter. Let's keep going though, because this problem has got a 4th degree equation. So we're going to need 4 derivatives. So we got to keep on going. So what's the 3rd derivative of this mess? Well, the 3rd derivative is this gets multiplied down front. That becomes positive 3/8. Notice it's a negative times a negative. 3/8. And then you subtract another one from our exponent. And so this derivative is 3/8 times, again, it's probably easier just to write it like it is, except again, I don't like negative exponents. So that'd be the square root of 4, which is 2. 2 to the 5th is 32. 32 times 8, woo, starting to get some big numbers now. 32 times 8 is 256. I'm sorry, I gotta write derivatives up here. I didn't write derivatives. Y cubed of 0. That'd be 3/256. Now, would you agree the cubed is very, like, what does that mean? Well, that's like the change of the slope. Notice it's kind of hard for me to understand that, but I'm just trying to make this match. I'm trying to make this match at the point 0, 2. I'm trying to make it match in every way possible. I want it to also go through 0, 2. I want its slope to be 1/4. I want the change of its slope to be -1/32. And now we get into an area that's kind of hard to understand. I want the change of the slope even to be accurate, 3/256. And then we get to keep going. Now, what are we going to do if we get out here to like the 9th derivative? Like we can't do this forever, right? We can't put those little hatch marks, those little tick marks. It works pretty good for first and second derivatives, but and third, but it's like by the time you get to the 4th, it starts to get kind of ridiculous, right? So a lot of times in math books, they'll start doing this right about here. Now, I don't like that very much because that looks like y to the 4th power. Does that make sense? So mathematicians are always kind of reusing symbols, but at least if you put it in parentheses, then it's not, then you wouldn't confuse it as y to the 4th. But that means the 4th derivative. So be careful because you'll see that in the book if you look in the book. So let's see, what's the derivative of that? Well, 5/2 would get multiplied by this. So that'd be -15. Looks like I'm going to run out of room because this is starting to get big. This is going to be 15/8 times 2 is 16. And now it's negative again. And then it'd be x plus 4. But then I'd subtract another one from it. So it'd be -7/2. So my derivative would be -15/16 times x plus 4 to the +7/2. And again, if I plug the number 0 into that, 4, the square root of 4 is 2. 2 to the 7th, I don't remember what that is. 2 to the 7th is 128, and then that's multiplied by 16. And so I get the slope, the change of the change of the change, or whatever one I'm on, is -15/16 times 128, which is 2048.
Hey, Doug,
Yes.
I think, could you go back to your previous model since we're doing the same graph, just real quick so I can see the equation for the problem?
Is that what you want to see?
Yeah. Is it, okay, never mind. I thought it was like 1/4 and 3/8. And I was like, it kind of looked like there was a pattern, but I guess not.
I see what you're good. I like the way you're thinking. So the thing that was the same is the y value was 2, the slope was 1/4, and then the change of the slope was -1/32. And then that resulted in these constants right here. So yeah, what you're wondering is, I wonder if we'll have those constants will be the same too. Well, we haven't gotten that far. So we got all of that information, and let me kind of go highlight it since we made all this. But where we really need to stare at, or what we need kind of for sure to be aware of, is this was the result of all this. Like this is what I needed to know. I know the point 0, 2 has to work in my cubic, whatever this cubic equation is that we're hunting for. I know 0, 2 needs to work in it. I know its slope at 0 needs to be 1/4. I know its second derivative. I know its third derivative. I know its fourth derivative. Now's where it gets really interesting. Now let's go find everything else. What's f prime of x? You get ahead of me and do this. We already have f of x. Let's copy it. Let's duplicate it.
Should we plug in the values that we got above?
Yeah, and then we're going to use those, but I want you to, this is going to get really easy. I'll show you why in just a second. just go find all the derivatives first. I'm going to catch up to you here, but I'm just. So there's our first equation. And what I want you to watch really carefully is what happens to these derivatives. So let's see if I take the derivative, and again, this is why, well, polynomials are so easy to take derivatives of, right? Aren't you really glad you're taking the derivative of a polynomial right now? Not of logarithm, not of the arctangent. I bet you don't remember what the derivative of arctangent is, for instance. We're taking the derivative of the easiest equation that exists. That's what's so powerful about this. So this is a power series, isn't it? Except for right now, it's just a power series that stops at 4 and n equals 4. But I'm gonna show you a pattern in a second that says, hey, this doesn't have to stop, and we don't have to work this hard. But you got to watch for the pattern, because here it's coming right now. So let's see, I take 4 and I multiply it by a, and then that x gets reduced by 1. I take 3 and multiply it by b, and then that x gets reduced by 1. I take 2 and multiply it by c, and that x gets reduced by 1. And I take 1 and multiply it by d, and the x gets reduced by 1, and the constant k is gone. And so there's my first derivative. Then I go onward and take the second derivative. Well, watch carefully. Here's this very important. Watch this. Now the 3 gets multiplied by the 4, and that becomes 12, and then this reduces by 1. And the 2 gets multiplied by the 3, which means this is now a 6. And the x gets reduced by 1. And then finally 2cx, that's just 2c. And then we proceed yet again to the third derivative. Again, watch this very carefully. 2 gets multiplied by 12, which makes that now a 24. And my x gets reduced by 1. And then 6 gets multiplied by x. 6 gets multiplied by b. My 6's and b's look the same. It's very not good. And then finally, we're at our fourth derivative, which seems like it needs to be black. I'll use the. And so we just get 24a for that. And I want you to think about this really quickly. Where did that 24 just come from? What did we end up doing to get 24?
I think it, can I say it or no?
No, I want you to say it if you see it. Yeah.
I think it's from the top, it's like 4 factorial, the exponent.
Is Martin right about that?
Did you multiply all of the exponents from the first function?
Yeah, like
Together.
didn't we start with this 4? That's what got here. And then because this got reduced by 1, it was 3. So we multiplied 4 by 3, and then we multiplied by 2, and then we multiplied by 1. We went 4 times 3 times 2 times 1 to get that. How do we get this 6 right here?
Two times 3.
It was first 3, and then it was 3 times 2, and then it was 1 times 6. It was 3 times 2 times 1. So that's nice. Now, we now have 4 equations. Now we have 5 equations. Which one should we solve? We have 5 equations. Which one shall we use?
Start from the bottom and work your way up.
Yeah, isn't the last one easy? Don't we know, my friends, from up above? Seems like we need a really cool color now. What color is it? It's got to be different. I guess we'll go with orange. Don't we know what that fourth derivative is supposed to be equal to? It's supposed to be 15 over 2048, isn't it? So doesn't that allow us to find a right now then? This is supposed to be equal to, wasn't it negative? Yes, it was. Negative 15 over 2048. So all I have to do is divide that by 24. I'm going to do this in my calculator so I get a fractional answer. If I say 15 divided by 2048 and then I divide by 24, I get some crazy decimal, but then I can say convert that to a fraction. Oh, it doesn't want to do it, so I guess I have to cheat. 2048 times 24. Didn't want to do it. So I now know, let's see, how am I going to do this? I think I want to squeeze.
It's negative 5 over 16,384.
Oh, does it reduce?
I guess.
12, 13, 14. Yeah, it does. It does divide by 3. Well, I think I'll leave it alone for now. Anyway, it might reduce and that'd be wonderful. And it does. So I got this, and then Eve correctly said it does reduce. Again, maybe you remember the trick. Does that bottom number, I know 15 divides by 5, but because of that 2, I know that number doesn't divide by 5. But I also know that 15's got a 3 in it. Does that bottom number divide by 3? The answer is yes, because 4 plus 9 is 13, plus 1 is 14, plus 5 is 19, plus 2 is 21. The sum of those digits is 21. 21 divides by 3, so I could reduce that. Now, this is the genius, though, of what value did we let x be here? It's very important. There's a hint.
0.
So if x is 0, then we get to do something wonderful here. I don't really want to do that. We get to say, bam, that's 0, which means that whole term goes away. And so, whoa, actually, we didn't actually need to do the last one first. We could have done any of these first, because don't we know that 6b, which is the third derivative, didn't we say that had to be 3 over 256? Yes? I'm getting a chill going down my spine right now. So all I have to do is divide by 6. And I get 1536 for that. And again, my friends, if x is 0, then I could have just went right to 2c, because 2c has to be the second derivative, which we said was negative 1 over 32. Oh, finally, I'm getting down into an area where I don't need my dumb calculator. So c is negative 1 over 64. Eve was looking for a pattern for this earlier. Did that number show up earlier?
Yeah, it did.
It was the a value, right? What was the a value? The a value was the number in front of the squared term, right? Is that also the number in front of the squared term? That's a c, right? Look at that. It's like it hasn't changed. So actually, I know the last answers, they're going to be the same. But anyway, x is 0. X is 0. Wow, this is great. All those terms just go away thanks to x being 0. I'm glad x wasn't 4. And so that leaves d to just be, well, whatever the derivative was, which was 1/4. And so I know d now. And from the start, we knew what k was. K had to be 2, since when we plugged in 0 for x, right? All of these terms are going to go away. That's always what the y-intercept was, right? So f of x had to be 2. So I now know all of my constants. Now we are there. I want you just to think back for a second. This is what produced this right here is what produced our a value, right? But what were these two things again? What were those? Like, what was that 15 over 2048 again? What was that? Where did we get that? What did we do to get that?
That was the fourth derivative.
Yeah, wasn't that the fourth derivative? So this was the fourth derivative. I'll write it this way. The fourth derivative evaluated at the point that we were interested in. And what did Martin astutely notice about that 24? Where did that come from? That was the fourth the factorial of 4. So to get our coefficient, isn't this our coefficient for what? Which one? What coefficient was that? It was this one, right? So it was the coefficient for our x to the 4th, our 4th degree term. Are you seeing a pattern here? 4 factorial, 4th derivative, 4th term. This is how we get, without doing the nonsense that we did yesterday and being limited to only equations that look right, this is how you find the coefficients for a power series. What was that coefficient right there? Ultimately, that A value, our coefficient, I cannot stick with that. Our coefficient is nothing more than the 4th derivative evaluated at 0 divided by 4 factorial. That's what you do. How do you get the third one? The 3rd derivative evaluated at 0 divided by 3 factorial. Isn't that what happened there? Wasn't this the 3rd derivative evaluated at 0? Wasn't that right there 3 factorial? This, my friends, is called a not just any old series, but a Taylor series. Now it's still a series. It's a geometric series. It's nothing new. It's still a power series. It's no different. It's nothing. We learned nothing new. It's still a power series, but this is how you find, this is the method that you use from now on to find the model. So let's see, how am I going to say this? Actually, let me show you a little bit more terminology. Let's first call this the other name for this, which is a Maclaurin. I can't remember how to spell Maclaurin. Did I write it down somewhere? Yes, I did. Maclaurin series. This Maclaurin series is distinguished by the fact that we use x equals 0. So this is what we just did. And so how do you find it? Well, think about what we just did. This first answer, if I write it in the normal way, this first answer was just f of 0. That's our constant term, plus then we have our x to the first term, plus then we have our x to the second term, plus then we have our x to the third term, and x to the 4th, and so on forever. See, we don't have to stop now because we see a pattern to this. How do I get the coefficient in front of the x? I take the derivative evaluated at 0 and I divide by 1 factorial. How do I get the second one? I take the second derivative evaluated at 0 and I divide by 2 factorial. How do I get the third one? Well, just keep going. I take the third derivative evaluated at 0, divide by 3 factorial. And I'll write one more. As we saw, the 4th derivative evaluated at 0 divided by 4 factorial. That's how I find the coefficients. So this will model, what does it model? Anything. It doesn't have to fit kind of a certain pattern. Models anything. Well, I do have to be able to take the derivative, right? Like the derivative or finding the slope, I have to be able to take the derivative, but remember we can take the derivative of anything. In my mind, this is the biggest or coolest takeaway of Math 253 right here. So here we go. Let's use this for something right now. So let's say that y was equal to the sine of x. Like, let's find a model for the sine of x. Notice that's a really easy derivative to take. So it's particularly nice if this is an easy derivative. And so I'd like to find a power series. I'd like to, and this is what I told you before, every single equation, no matter how weird it is, can be replaced with just, well, squared equations, cubic equations. And of course, we need to watch this in action. Speaking of watching it in action, we never even looked at the last one, did we? We'll just say it's true. We'll look at this one. Okay, so what did I just do? So what do we, well, does it make sense we have to decide how many terms we want? You know, how good do we want our model to be? Well, I don't know. Let's just start into it and see. Let's see what we need. Well, let's go find all of our derivatives. So again, we're saying I'd like this to match at x equals 0. This only works for x equals 0. So I know what y of 0 is. The sine of 0 is 0. So let's just progress. Y prime, the derivative, this way. Y prime, you know what the derivative of sine is? It's cosine. And so what's the cosine of 0? Remember your unit circle. This is important. Cosine is what coordinate?
X.
Cosine
It's 1, right?
x. And so the cosine of 0, 0 degrees is right there, and the x coordinate of that is 1. And so it's actually 1. So you're right, Eve. And sine is the y coordinate. And if I'm at 0, and notice we're always there, the sine of 0 is the y coordinate of that point. Well, the y coordinate of that point is 0. Again, bust out your calculator. Sine of 0, cosine of 0. Progress. Second derivative. The derivative of cosine is negative sine. What is the negative sine of 0? Well, the sine of 0 is still 0, so it's actually 0. Notice this is interesting because that means some of our coefficients are 0, like they're not going to be there. Like there's no, what is that? Squared term, cube term, like no cube term, no squared term, like there's some terms missing. Isn't that kind of fun? What about the third derivative? What's the derivative of sine? It's cosine, and the negative just kind of comes along for the ride. And so the third derivative, cosine of 0 is 1, but then there's a negative there, so it's negative 1. What's the fourth derivative? Derivative of cosine is negative sine, but then negative times a negative. Hey, look, we got our sine back again. We're actually back to our original equation now.
And we're stuck in the paradox.
We are now chasing our tails. The derivative of sine, or the sine of 0 is 0. So notice every other one of these is 0. Let's keep going. Y, the fifth derivative, the derivative of sine is cosine. Do you see how they're going to repeat now? So I can actually go really fast. And so the fifth derivative evaluated at 0 is the derivative or the cosine of 0 is back to 1 again. So cosine is interesting because it's like cyclical. Do you see how this went from 0 to 1, and then 1 to 0, and then 0 to negative 1, and then 1 to 0? Like this just started over again. In other words, this is kind of where the pattern, I'll erase this one. This is where the pattern actually ended right there. So it went 0, 1, 0, negative 1. Well, that pattern is just going to continue now. Do you see that? I'm just seeing the first part of it. What happened right here? 0. Then 1 happened. And so I already know the next one's 0, and the one after that's negative 1. So it's kind of cool because I actually don't have to work so hard, because I can make up equations that have horrible derivatives, right? Like what about natural log of the tangent of x? Like that's going to be a fun derivative to take, right? Especially if we have to do it 9 times, right? So this is a particularly good place to start. Okay, well, we're all set. Let's go find the model. Let's go find the Maclaurin series. Extra credit. Why is it called the Maclaurins? I don't know the answer to this. There's a Taylor series, which I'll get to. I guess probably Monday since there's 10 minutes left in class, but why is it called the Maclaurin series? You know, when was this figured out? Was Maclaurin the person that invented it? Was the Maclaurin named for it posthumously because he was a brilliant mathematician, or she, and didn't get any credit. So somebody named it after him. Is it like someone's dog? Like what's the Maclaurin series? Well, on to our model, our power series, just a power series, nothing new. We're not doing anything different. What's our power series model? Well, we just found the pattern to this. All we have to do is say, great, here it is. This is easy. And notice it actually makes sense to not start like we did back here. I decided, let's find a 4th degree polynomial for this. And you're used to writing the 4th at the start. But if we haven't decided how far we're going to go with this, does it make sense why you'd kind of want to start with the constant side? That's why we've always been starting with the low side, because it's like, well, how many terms do you want to add? So I'm kind of saying I'm going to put that off for later. So I'm going to start with the constant. So because that first coefficient was 0, and that's x to the 0, if you will, by the way, divided by 0 factorial, which is annoyingly 1. Then our next coefficient is 1 divided by, remember, divided by 1 factorial. So it's this 1 divided by 1 factorial. And then our next term will be this term, 0 divided by 2 factorial. Our next term will be this one divided by 3 factorial, right? So it's the, remember, it's the slopes. It's the slopes divided by their factorial. Slope of the slope at second derivative divided by 2 factorial. Third slope divided by 3 factorial. So
Is this actually an alternating series
yeah,
in a way?
cool. It's not in a way, it just is. So I'm glad you pointed that out. So to fill in some of my rest of my terms, this is the x term, and this is the x squared term, and this is the x cubed term. And then the 4th degree term is gone because of the 0, but I want to write it in here anyway, just so you're kind of watching the pattern happen. Over 4 factorial. So because of that 0, there's like no reason to even write this one, right? And then the very last term is back to 1 again. So plus 1 divided by 5 factorial, x to the 5th. So because of the 0 terms that I will now kind of go whoop, whoop, whoop. Notice f of x is more cleanly written as 1x. And then 3 factorial is 6. So that's 16x cubed. And then 5 factorial, I think, is 120. 12. I'm drawing a blank. I don't think it is 120, but it seems like it'd be 60, but it doesn't. This doesn't sound right for some reason.
It is 120. I just did it.
Yeah, okay. It is 120 plus 120. So yeah, this is actually an alternating series. So notice it went plus, minus, plus. The next term will be minus. I know it will be x to the 7th. Can anybody tell me how to figure out what the coefficient is going to be?
It's going to be negative 1 over 7 factorial, isn't it?
That's exactly right. So sign is kind of interesting because notice the numerators are always just 1s and negative 1s. There's 0s, 1s, and negative 1s. And so it just alternates from 1 to negative 1, 1 to negative 1. And so we're sort of going up by odd powers. So does it make sense? I could even write the next term in here, which would be plus 1/9 factorial, whatever the heck that is, and then it'd be x to the 9th. And so see how easy it is? Like we could just keep adding and adding and adding and kind of going forever. That's kind of cool. Now, here's where it gets really fun. Watch this. So, wow. So what you're saying, Mr. G, is you're saying that this is a model for a sine. You're telling me there's a polynomial equation that models a sine wave. There's no way this is going to be true. X. So there's a sine wave. You're used to seeing that. Now let's watch it grow. So our first equation is there. Now, again, do you agree if you're going to pick a line, that's a good model? That's the best you can do. All right. But what if we, as we've been doing in the past, start adding terms to it? Well, the next one is -1 divided by, I guess we'll call it 6. I was going to call it factorial, but let's call it 6x raised to the 3rd. Is that an improvement? It improved when I added another term. Now notice one thing that's interesting here is, and this might come up in your assignment, but notice this model, this power series only has 2 terms, but it's cubic. So your problem could say, I want the first 2 terms. That doesn't always mean it's squared or whatever, like, because sometimes you could have terms that are missing. So this is actually a cubic model. And notice it's interesting, like the squared is left out, like there is no squared. And there also was no constant. Isn't that interesting? And so that's even a better model. And notice it kind of hangs tough, like it just stays closer to the, remember the right answer to this is the red parabola. And so it just hung out closer longer, right? The blue started losing it around 0.4. But notice our cubic equation hung tough clear down to like 0.8, right? So this is just getting better. This is very exciting. So let's add another term. That term was 1/120. 1 divided by 120 was positive. Whoa, what are you doing? 1 divided by 120, x to the 5th. Somehow I snuck a 1 in there. How in the world did I manage that? Yeah, look at that. The purple graph even hugged it, if you will, a little longer. Notice the purple graph seems to be good out to about 1.6. It's just getting better. Can you see that a polynomial, like doesn't a sine wave actually kind of have that hoop-de-doo looking polynomial look to it? This is kind of cool. It's just getting better and better. So our next term is plus, and I think I wrote that one down. No, it's actually minus, right? It alternates, like Eve said. It's 1 divided by 50/40. And notice 1/50/40, like that's a small number, right? Does it make sense those coefficients are on their way to 0? Like do you agree that 1/50/40 is making this term less important, if you will? Wow, look at that black one. Notice it hung tough even longer. Doesn't it look like it's good out to about 2.5 now as an estimate? So if you wanted to know, now again, put yourself in the place of Archimedes, who had like chalk and wrote on the back of a piece of bark or something. And Archimedes would like to know, what's the sine of 2? How are you going to get the sine of 2? Well, look, multiplying and dividing will get you the sine of 2. Do you see how amazing, how powerful this power series is? All you got to do is multiply and divide, and you can know the sine of 2. Can you appreciate that black curve is going to give a darn good answer for the sine of 2? Look how close those are. Look over here on the side. What our scale is. That's a darn good answer. And all I got to do is just keep adding terms if I would like my answer to be better. I'll add a few more. Except this time I don't know the answer, right? So I'll say, what am I going to say? 1 divided by 9 factorial. Fortunately, you can actually just type an exclamation point, and Desmos is programmed to understand that doesn't mean 9. So that's cool. Uh-oh, got excited. So that one just turned red, so I got to change the color. We're not going to be able to see it. Idiot, what are you doing? Orange, we haven't used that one yet. So I'll turn off the first couple because maybe they're distracting now. So black was pretty good, right? But notice orange is better. Notice orange would give you the answer to the sign of 3 because it's staying there a little longer.
So did they figure out the power series and then created sine of x to model the power series? Or did they find sine of x and then create the power series to model
That's a good question.
the sine of
I
x?
guess, and again, this is what my historical extra credits are always about, is looking into those things. My guess is people realized that in a right triangle, the opposite over the hypotenuse, if the angle stays the same, like 32, if you pick a 32-degree triangle and it's teeny, 32-degree triangle and it's large, the opposite over the hypotenuse is still the same answer, right? Just like in a circle, the circumference divided by the diameter, no matter what size it is, 3.14 every time. So if you have a 32-degree right triangle, no matter what size you draw it, huge, small, opposite divided by hypotenuse, it's always the same answer. And you can actually just draw a right triangle accurately with a protractor and actually measure those two and divide them and get a pretty close answer what the calculator tells you. My guess is they knew about what that number was. And remember, they just called it sine, like they just made a name up for it and said, sine takes the angle and it tells you what that ratio is. But it's like, how are we going to come up with a machine to do it? Do you understand that what I'm showing you right here is the reason you have a calculator that tells you that answer? Because sine is opposite over hypotenuse in a right triangle. Like how do you know what that is? Again, you and I, myself included, I'm like the youngest person that still takes this for granted. I sat next to a dude at a table one time that was 80 and he was an engineer, except for when he was an engineer, he had a slide rule because there's no such thing as a calculator. So what made him an engineer is he figured out how to slide the two stupid sticks past each other and figure out what the logarithm of something was. And so I was kind of like the first generation. I think in the 6th grade, there was a calculator. The first one, it was like this big and it cost like $50. But I think, and I'm not sure about this, but I think this is the reason you have a calculator. Because would you agree that this last example I just gave right here allows you by add and subtract. Computers are really good at add and subtract. It's not hard to program things to do add and subtract. Well, you can now use this if you want to know the sine of 3. Notice it doesn't work very good for the sine of 10, right? Is the orange graph next to the red graph by the time you get out to 10? No. The radius of convergence thing is kind of important. Now, let's try one other thing, and then we'll get out of here. Who's smart enough to write this in sigma notation, right? Because I don't want to, every time I just added a term, I had to type it in, right? So can we use, thanks to Eve for pointing this out the other day. Could we write this in sigma notation?
Well, we're going to have an alternating sign. So
Good job. So how do we do alternation? How do I make it alternate? What do you do to make it alternate?
-1 to the n power.
Beautiful.
And would that be over n factorial?
Yeah. And then now, is that working correctly? Because do you understand? We got to get it to alternate correctly. Do you agree the first term is supposed to be positive, and then the second term is negative, and then the third is positive? It's either n or n plus 1. Is it -1 to the n, or is it -1 to the n plus 1?
Well, our first term is positive, so I think it'd be +1, right?
Let's play with that and see. So do you agree that we have our nth term, and then we just have to take this whole thing, as Eve correctly said, and divide by n factorial? Is it working? Is that right? Notice that blue curve. I'll turn these other ones off so we're not distracted. It's like, well, that's not right.
Not working.
Why is it not working?
Needs a +1 on the alternation.
So maybe it's a +1. Maybe that's not n. Maybe that's n+1. Oops. Come on, man.
1, 2.
It's not working. Why is it not working?
You need parentheses, I think.
Parentheses.
I'm sorry. Still not working. Why not? Look at your coefficient. Look at your exponents. What are the exponents? N goes from 0 to 9, which means 1, 2, 3, 4, 5, 6, 7, 8, 9. Do we have all of those? Well, no. We have x to the first. I'll write it in here so you can see it. We have x to the first, x to the third, x to the fifth. We don't have an x to the second. We don't have an x to the fourth. Isn't our summation here giving us all of those? We somehow need this to be not 1, 2, 3, 4, 5, 6. How are we going to get that to be 1 and then 3 and then 5 and then 7? Because right now it's 1, 2, 3, 4, 5. It's given us every single one of them. Do you understand that? That's why it's not working.
Also, I feel like it's messing up your alternation. Because if we had -1 to the n+1, then 2 would be negative and not 3,
Yeah.
right?
So just to stare at one of them, we need cubed to give us a negative, right? Cubed. So when n is 3, when n is 3, then this would be 3 + 1, which is 4. And then the 4, when you take -1 to the fourth, that makes it positive. So you're right, that isn't. How do I get this to work? Well, here's a hint. 2n. Now, if you put n as 1n, it becomes 2. And if you put n as 2n, it becomes 4. If you put n as 3, and it becomes 3. Do you see how, I'm sorry, it becomes 6. Do you see how that would make it go, the exponents be 2, 4, 6, not 1, 2, 3, 4, 5, 6? Except for that doesn't work because it's 2, 4, 6. I need the odd ones, right?
You do -1 now.
Maybe -1. Let's try that. That doesn't appear to be working. Let's see, x is 0. If x is 0, that would make that, I'm sorry, n is 0. If I put 0 in, that'd be 2 times 0, which is 0, and then that'd be -1. So that'd be -1. This is x to the -1. If I'm starting at 0, but I need my first term to be x to the 1, how do I get that to be 1?
Can do 2n plus 1.
Plus 1, maybe that will do it.
Please do 0. Or change it to 1. And I think we need to do that for our n term as well, right? The factorial term. I mean,
Yeah, now notice if I put 0 in for this, do you agree that this gives us x to the 1 power? It gives us this one, right? But that was supposed to be 1/1 factorial. But if we do that, then if I put 0 in here, then I got 0 factorial. You see what I'm saying? Like we're the coefficient is not matching up. Like I've got this now correctly starting at x to the 1. So it's giving me that first term correctly, but it's not giving me the right coefficients, right? It needs to be, if this is x to the 1, then this needs to be 1 factorial. So yeah, don't I need to like up this by 1 as well?
Yeah, but your x to the power of x is still not right, because if you put 2 in, you have 2 times 2, which is 4 plus 1 is 5. So you're still missing your 3.
No, because if I move from n as 0, I move to n as 1. That's my next one.
Oh,
N is 1,
sorry.
and that give me x to the third. So notice it still isn't working. Like we're close, but it's not working. Like it, I mean, I have 9 terms here and it's not matching up very good, right? Well, let's think about this. So I put n as 0 in. The bottom is now 1 factorial. This is x to the 1. But is this alternation working correctly? Does this also need to be 2n? or perhaps 2n plus 1. You see how hard this is? Like this is not easy, right? Like you're pondering this, you're wondering. So because we're out of time, I'm going to fix this. Boom. And there's the right answer. I would have let us play more, but it's like 9:30 right now. Now it gets fun. Because what if I change this to 12? Notice how it just gets better. Do you see how that's working out to 10 now? Now I can find the sign of 10. We already know this is going to panic, but let's throw a 3 in there because remember, it's actually got to add 32 terms to this. So it takes a second. Look at that. Whoa. Now it's accurate out to 25. What's your thoughts on the radius of convergence of this? Notice it's just getting better and better and better.
It could be infinity if you set it to infinity.
Yeah. Remember what we're saying is this 32 is not really 32, it's infinity. If that's infinity, this is a sine wave. You understand that? Like there is no radius of convergence. The radius of convergence is infinity. As long as you have enough terms, you can plug in anything you want. So with 32 terms, we would agree we're fine out to 25, right? Or 24. So, wow, now this is getting amazing. Isn't that crazy? We're actually modeling a sine wave with a polynomial. Like, isn't that insane?
That's weird.
This is a terrible idea, but I'm going to type 64 there now. See what happens. Seems like, what, wasn't it going to take twice as long, I guess? It's nice to see computers actually taking some time with things, right? We're all lazy and spoiled. We expect everything to be like, what's wrong? It's like, give me a second, man. I'm adding 64 terms. So notice that took it out to like 33. But you can see where this is going, right? Like I got to shut up here, but it's like, and notice it's having trouble. Like look at the graph down there. It's got all shaggy or something. I don't even know what's going on there, but it's like it starting to struggle. Like it isn't going to let us do this much longer. If I tried 100, I think it's going to just like shut off or something. Unbelievable. That's a perfect model. So that's what we're going to do. We're going to pick it up here with more discussion on this on Monday. So I'm still teaching you 3.11.3, which means 11.3 is not due. Whoa, what the heck is that? So it already freaked out, right? So that's not real. Like what just happened right there? I don't know what that is. I think it just, blood just started coming out of it. Like it just died.
Too many terms.
Too many terms. It's just like, I can't handle this anymore. I get it. Keep in mind, in order to do that, it had to go 1 over 64 factorial. Try that on your calculator, 64 factorial. It's a really big number. I don't even know if your calculator will tell you what 64 factorial is. It's such a big number.
1 to the E86.
86. That was actually close to not making it. Your calculator can only tell you the E to 2 decimal places. So if you take it out to like 66, 67, 68, somewhere in there, it's going to say error because it can't do it now. Because there's only 2 decimal places for that 10 to the power of thing. So unbelievable. We have a perfect model. So I think this is why you have a calculator. That's kind of my point. If you decide to take the sine of 2.179854682, does it make sense? Probably no human in history has ever wanted to know the answer to that. So it's not like all those answers are stored in your calculator. I think it's plugging 2 into, well, a polynomial like this. It's giving you an approximation for it. So this is the power of this. This is unbelievable. So what you're telling me is all this time, you mean sines and parabolas were the same thing? That's the beauty of math, is the connection and order to all of this is just breathtaking. You don't have a chill going down your spine right now. You're something wrong with you. All right, we'll keep talking about this Monday and begin modeling other stuff. We'll model natural log and we'll model cosine, we'll model tangent, we'll change everything. That's what this section is really about. Books ruin this, but we're just going to play some more for a couple of days with this and make sure you can do this. It's actually not hard, is it? Like all you're doing is taking a derivative and dividing by a factorial. It's like this is way easier than 11.1's assignment. This is really easy. All right, that's my record for going too long. Sorry. As always, if you don't have to leave and you want to ask questions, stay after.
Thanks, Doug.
Bye. Thanks, Doug.
Thanks for hanging out.